Okay, welcome back, everybody. Hopefully you were able to enjoy the long weekend. So today we continue in this class, and we are going to talk finally about supervised learning. So until now, we introduced machine learning and we discussed maximum likelihood estimation. And now we will, or most of this lecture will be focused on supervised learning, which, as I said, is the major part of the course. So roughly between a third and half of the course is going to be on supervised learning. We will finish some of the stuff that we didn't on maximum likelihood estimation, and then move to supervised learning classification. Before that, a few announcements. So first of all, we're going to have another recitation. So we had a recitation on Friday. We're going to have another recitation this Friday. Still, I think, more general introduction. Problem set 1 is going to be released. Daniel, you haven't released it, right? I mean, at the end of this class, we said?
Yeah, right after this class, it will be released.
Right after this class, great. So problem set 1 is going to be released. As I mentioned at the introduction, when I first, on the first lecture, problem sets are going to have a mixture of programming and theoretical questions. So we'll have, usually we'll have 3 or 4 theoretical questions and 1 programming question. And this is what you will see in this problem set. Daniel posted online, but I just want to say that in the past, and my experience as a student, it's very useful and recommended even to work in groups. So we don't want, or you do not need to work on the problem set completely on your own. You're more than welcome to form study groups. Of course, it's a bit challenging how to organize these online. In the past, people were just sitting, but we're definitely, permit it and even encourage it. You do have to report, and you will see in the problem set, you do have to report who you worked with. That's not, there's no problem with that, but we do want to know who worked together on the problem sets. But other than that, I recommend it. I think, well, if you feel like you can do it easily on your own, that's fine. But generally speaking, it's good to work with others on these problem sets, and we allow it. As long as you write your own, of course, you have to, at the end, you will see the instructions, but you'll have to write, of course, the solution on your own and tell us who you worked with on the problem set. Okay, so this is for the problem set. And again, if you have any questions about that, of course, you can ask on Piazza. Going forward for this class, if you have any questions, please post to the chat, and one of the TAs or Daniel will alert me, and we'll call on you, or they will ask the question for you. But yeah. Okay, good. So let's start with the lecture. And as I said, the first thing I want to do is finish the maximum likelihood estimation part. So in the last lecture, we talked about density estimation. Initially we talked about maximum a posteriori or Bayesian-based estimation, and then we moved to talking about maximum likelihood estimation. And I mentioned that for the most part, we will rely, or for the most part in this class, whenever we will have a probabilistic model, we will primarily rely on maximum likelihood estimation. And the idea of maximum likelihood estimation is to represent the likelihood of the data given the model. And that could be very, I mean, the exact format of this likelihood function can vary depending on the model you have. So you can have a coin flip model where each flip is independent. You can have something called the Bayesian network where things are partially dependent. You can have a fully dependent model. It doesn't matter. As long as you can write your likelihood or the probability of the data given the model, you can employ the maximum likelihood principle. And the maximum likelihood principle basically tells us that we want to find the model, in this case, the parameters of the model, that will lead to the highest probability or the highest likelihood of the data given the model. Okay, and we showed an application of this idea to coin flip, right? So we derived the maximum likelihood estimator for the probability of heads if we have n1 heads and n2 tails in a coin flip, and it came out to be just the count. So basically the number of heads divided by the total number of times we flip the coin. So that's the result, but maybe you would have expected it, but this is the maximum likelihood estimator as well. It's not just some count. It's really representing the value that will lead to the highest likelihood of the data. Okay, so this is what we discussed. Okay, so this is what we discussed. Now I want two more things, and then we'll finish with this one, with this part. One is that in many cases, rather than maximizing the likelihood directly, it might be better to maximize the log likelihood. Now, the outcome is going to be the same, in the sense that the model that you will select, the probability for heads, for example, is going to be exactly the same if you maximize the likelihood and if you maximize the log likelihood. Why is that? That's the case because log between 0 and 1 is an increasing function. Okay, so if you have something that and of course the probability or the likelihood is always between 0 and 1, right? The product of probabilities is always between 0, each probability is itself between 0 and 1, and the product of these values is also between 0 and 1. So the likelihood function, the likelihood of the data given the model is always going to be between 0 and 1. In that case, anything that maximizes the likelihood is also going to maximize the log likelihood and vice versa. So if you walk in log space or in real space, of course, the value, the likelihood itself, the log likelihood and the likelihood are going to be two different values. But the parameters that maximize this function are going to be the same. And we don't really care about the likelihood, or in some cases we do, but in most cases, the thing that we care about the most is the parameters. And the parameters will be the same. So if you, instead of maximizing the likelihood of the coin flip, you maximize the log likelihood, you will still get the same parameters. And again, for coin flips, this is not really useful because we can do it without it. But there are some probability distributions, including some that you will work on in the problem set, but also even a density estimation of Gaussian distributions, right? So this is maximum likelihood in Gaussian or normal distribution, where it's much, much easier to work in log space. And I'm not going to do the derivation. You will do something similar in the problem set. But generally speaking, the result would be the same, but sometimes it's much easier to work in log space, for example, because in log space, all products become summations, especially if and sometimes we have something e to the power of something that goes out and so forth. So you can think of a lot of advantages to working in log space. And again, the reason why we are allowed to work in log space is because the values are always between 0 and 1. So anything that maximizes it in the probability space will also maximize the function, or any value that maximizes the function in the regular space will also maximize it in the log space. Okay, so this is basically it for maximum likelihood estimation. Again, writing the main idea is writing the likelihood as a function of the model, basically the probability of the data given the model as a function of the model, and then trying to find the value that maximizes this function. And usually taking the derivative, sometimes you need to take the derivative with respect to this, as we showed, either in real space or in log space, and basically you get out the value that maximizes it. Okay, good. So I don't know if anybody posted the question, but right. So I'm not going to do the derivation for this. You can try it, or in the problem set you will work on something even more challenging. So you will get to exercise with maximum likelihood estimation derivation. So just really to summarize, right? So if we discussed two ways in this lecture in the previous and current lecture to estimate parameters. One is based on something we called MLE, and the other is called MAP. And both of these use the probability of some likelihood function. The difference is that in MAP, right, we use some prior on the data. So the parameter that we obtain is affected not just by the data we observe, but also by some prior belief we have. Right? And again, the impact of that prior belief usually is a function of how much data we collected. If we collect a lot of data, then the MAP estimate is not going to be affected too much by the prior. The prior has a limited impact. If we collected relatively small amounts of data, then the prior has a big impact. So that's the MAP estimate, maximum a posteriori. And usually, again, it's the argmax of the probability of the data given the model times the probability of the prior probability of the model. And the other direction we mentioned, which doesn't require any assumption, so we don't need to assume, we need to assume the probability distribution, but we don't need to assume any prior on the parameters, is the MLE, and the MLE is just defined as the argmax of theta, of P of D given theta, or the likelihood of the data given the model. Okay, so this is the two options that we have. As we said, or as I said, in many cases, we prefer to use MLE, not maybe because it's the more accurate thing, but just because we don't need to make, or we make much fewer assumptions in MLE. We don't need to have any prior estimation of the data, of the model. And in many cases, we can collect, especially for density estimation, we can collect samples. So again, we'll get to that and how complicated it is to connect enough samples for density estimation. But for now, the assumption would be that we collect enough data to estimate the probabilities. Okay, so I don't know if there were any questions. I didn't see anything in the chat. So if there's no questions, then let's turn, that's something I should say. As I mentioned, I asked everybody to have Piazza ready. So please open Piazza. I'm going to release the quiz, a few questions for you on maximum likelihood estimation. You will do them, and then we will discuss the results. Okay, so I'm releasing 3 questions. And I should say, I mean, this is the first time we are doing this. These quizzes are not graded. In fact, they're anonymized, so I don't even know who is answering what. I do get statistics for the class, so I can see if people on average got it right or wrong, but we don't follow individual responses, so don't treat it as an exam or you're not going to be graded on it. I do want you to take it seriously because it helps me and I guess the instructors see if whatever we discussed is understood, so it's a nice way to gauge your your attention and also your understanding in a quick way, but it's not meant to test you in any way. Okay, and then sometimes there are some interesting points that I highlight after we stop them. So take a few, I don't know, take a few minutes and try to do them. Hopefully everybody can log to the Piazza, and there are 3 questions on Piazza on maximum likelihood estimation. Yeah, and I see that some people have already started doing that, which is good. Okay, so a few more seconds, please try to answer. Again, no grading, so yeah. These are polls, they are not quizzes, I agree, yeah, sorry. But yeah, the goal is to. Okay, so let's start discussing these. Let's see if we can share the screen. Good. Okay, so this is the first question I asked you. So this is about maximum likelihood estimation for coin flips, exactly what we derived, and some questions about the probabilities that we can get. So we performed n coin flips, and the key part of this question really is that you have to assume that Q is between, or the estimation that we had is greater than 0 and less than 1. What does it mean? It means that we had at least one head and at least one tail, right? If everything was heads, then Q was 1, and if everything was tails, Q was 0. So we know that that's not the case from the observations, because we know that Q is between 0 and 1. So whatever we estimated was between 0 and 1, so not 0 and not 1, meaning that we had both head and tails. Now, we performed another coin flip, and the question is, what's the new probability that we estimated? Okay, so what would be the new probability? We can easily work this out, right? We know the answer. Right, so if I want to write, let's say we had before N1 heads, what is the new probability for heads? Anybody can, let's say that we got heads now. What's the new probability for heads? It's going to be N1 plus 1 over N plus 1, right? Everybody sees that? And before we had N1 over N. Now, because we know that N1 is not equal to N, we just said it, this must be bigger. And similarly, if we had tails, then this would be the probability for heads will be now right, which is basically right. So this is obviously bigger. Okay, so whatever we got, heads or tails, the probability will change. We don't know the direction because we don't know what was the outcome, but we are guaranteed that the probability is going to change, whatever the outcome is. Again, the only way it would not have changed if we had all zeros and got another 0, or if we had all if we had all heads and got another head, or if we had all tails and got another tail, which is not the case. We know that we had at least one head and at least one tail before. So in this case, the answer is answer 2, which most of you got correct. So it doesn't depend on the actual value of Q and the new observation, as long as we know that Q is between 0 and 1. Okay, so this is the first answer. Let's see. Let's go to the next one. 2. Okay. Okay, so now we perform 2 coin flips and learn the probability of heads. Now things are a bit more complicated, because as we said before, if we know that it's between 0 and 1, so we don't know if there were, but there is one case here where, so we know that if we got 2 heads or 2 tails, it will going to change. But if we get 1 head and 1 tail, there's going to be one case where the probability is not going to change. What's that case? Anybody? So there's only one case where the probability is not going to change. Let's see if someone does. Yeah. Yeah, 0.5, not 0.6, but yeah, that's correct. So basically, if we had 0.5, Like if we had 50-50 and we have one more of this and one more of that, that remains the same. Of course, the probability remains the same. Any other thing would change. So the answer in this case is 3, that almost all of you got correct. So the answer here is 3. What about this thing here? So here, that's a bit more tricky. So here I'm telling you that what we discussed before, that we have 50-50 cannot happen because we know that Q is between 0.6 and 1. Basically, we know that we had at least 60% of heads before, but we didn't have only heads. We had at least 10. So now it doesn't matter what outcome we will get, right? So we can just do the I mean, obviously, if we get so obviously, if we get 2 heads or 2 tails, obviously that will change the estimation. The question is what will happen if we have 1 head and 1 tail, 1 head and 1 head and 1 tail, yeah? And the answer is that in that case, the new probability is n1 plus 1 over n plus 2, right? That's the new probability for if we get, right? But if n1 over n is more than 0.6, then this will be less than n1 over n. Okay? So if we know that n1 over n is already 0.6, then this will not, this fraction here will be less than this. Okay, so the answer in this case is that they're going to be different. So the answer in this case is 2. They're going to be different, as most of you were able to correctly say or correctly find. Okay, good. So this is the solution to this relatively simple quiz or poll, and basically that's the idea of MLE, that we can recompute MLE when more things come in. Sometimes the result will change, sometimes they will not change, but it's not always easy to say. Okay, so this is a maximum likelihood estimation. I don't know if we have, I don't see any more questions. Okay, so in that case, we are now moving to our next topic, or basically starting our next topic, which is going to be supervised learning or classification. Okay, so classification is one part of supervised learning. It's not the only part. There's another important part which is called regression, and we'll get to that, and then we'll go back to classification, because some classification can use regression and some classification does not use regression. But today we are going to talk about classification. Classification basically means that we have a set of potential outcomes, a discrete set of outcomes, and we want to assign each sample to one of these outcomes. For example, if we want to classify cats and dogs, we want to say this image is a cat and this image is a dog, or maybe this image is a car and so forth, so we can have multiple images. Okay, so we did density estimation, and today we are going to predict the category or a label. And there is another thing called regression, which is also supervised. So again, we'll discuss what supervised means in a second, but this is also supervised, and this gives us a real value output. Okay, and we are not going to talk about today. We'll get to it in a few lectures. Okay, so as I said, classification, for example, or one example of classification is image classification, a very important problem that a lot of people are interested in, or of course online and so forth. So for example, in this case, if we want to classify cats and dogs, how do we train a model that, given a new image, can tell us whether this is a cat or not? Okay, so one way to do it is to use what we learned already in probability, and this is to estimate directly the base decision rule. The reason I'm bringing this up is because this is a theoretically very useful procedure. The big challenge with this idea is, how do we put it into practice? How do we learn probabilities for different samples and for different classes? But if we have a way of learning probabilities, as you will see, we can make almost a perfect decision on the data. Now, I'm going to discuss this a bit theoretically at this stage. So I'm not going to show you how to learn the Bayes rule. I'm just going to tell you that if we knew it, we can use it. And then later in the class, so today we are going to show one example of using or of actually instantiating or finding an example of using Bayes decision rule. And we will also use it in other classes, for example, in naive Bayes, to do classification. So again, now it's a bit more, I would say, theoretical exercise about if we knew how to do it, then this is what we get. And later we will discuss how to actually do it. Okay, that's why I'm presenting this today. Okay, so what is the idea of Bayes decision rule? Remember, our goal is to classify. So we have basically a set of possible outcomes for Y. Y is the class label, right? So like Y can be cats or Y can be dog. And X is the samples. In our case, the samples are images, but you can think, for example, if you want to predict if a stock is going up or down, maybe the sample will be the price of that stock in the last 7 days. Or if you want to predict if someone is a male or a female, maybe the input would be the weight and the height. I mean, you can think of a lot of different ways, of course, to represent the input. So our goal is to predict Y, right? Predict the label given X, right? If we use Bayes rule, then the probability of Y given X is X given Y times P of Y divided by P of X, which we will call Qi of X. Qi because this is for class I, okay? Now, in some cases, we cannot make a strict decision. For example, if I want to predict whether you're a male or a female in this class, given your height and weight, there are cases where basically the same height and weight will, or both male and a female will have exactly the same height and weight. That's not only possible, it happens a lot. So in that case, the best I can do is talk about the probability that you are a male or a female. I cannot really say, there's no classifier that will actually give you the correct answer. But in that case, you can still give a probability for a male given these values and for a female given these values. And maybe you will get different probabilities and you will take the one with the higher probability. You will not be always correct, but on most cases, you will be correct. So this is called the Bayes decision rule or the Bayes classification rule. The classification rule says that we compute the probability of Y given X or the label given the sample for both classes, or if we have multiple classes, we can compute it for 10 classes, it's up to us. And then we select as the prediction, the class that has the highest probability, right? So for each class, for each sample, we can get the probability for each class, and we select as the prediction, the class that has the highest probability. Okay, so this sounds like a good idea because, as we said, there's not always a way to tell completely from the data what is the right outcome. Sometimes there could be the same sample, or the same sample can have actually multiple labels. So we want to find the one that has the highest probability. So this is a good way to do classification. Of course, the real challenge is how do we compute these probabilities here, right? P of X given Y and P of Y. If we knew how to compute them, then we would have, in some sense, the optimal classifier, because then we can compute the probability for each of the classes and select the one that has the highest probability. The problem is, of course, that it's very hard to compute. That's some of the algorithms we'll discuss, including today, are actually about or trying to exactly do that, trying to estimate these type of probabilities from the data, and with more or less success, depending on which data we have and which method they're using. Okay, so again, the idea of Bayes decision rule is we compute the probability for each of the labels given the sample, and then we choose the label that maximizes this probability. There are some advantages for this. So we will talk later about generative and discriminative classifiers. This is a probabilistic. If you don't necessarily need to use probabilities for classification. As I said, you can just make a decision. But one advantage of using a probabilistic classifier is the fact that you can also talk about confidence, right? Because now you have the probability for class 1 and you have the probability for class 0, and you can say, what is the ratio? What is the confidence that, or how much more confident you are that this is the right label compared to this? For example, in the height weight, maybe there are combinations of height and weight that we are very confident are female, and maybe there are combinations that we are very confident are male, but there's a lot of them that we are not so sure. So now, rather than just saying with higher probability you're male or with higher probability you're female, I can also tell you that with higher probability you're male, and I'm pretty confident, or my confidence in this is X. And again, I'm not going to go into exactly how to determine confidence. That's not the goal of this class, but in statistics, there are ways to define confidence based on the probability values that you assign to different labels. Okay, so that's an advantage of using a probabilistic way of classifying. And you can use it for some tests like yield ratio and so forth. Okay, just as an example, right? If we have a point in this case, right? If we have, like, let's say 2 Gaussians and we have this a triangle here, right? So basically the triangle is in the same location. Let's say this is class 1 and this is class 2, right? If the Gaussians have one type of distribution, in this case, very centered around the mean, then we will say, yeah, this is probably very likely to belong to class 1. It's very unlikely to come from class 2. Here, we will still assign it to class 1, okay, in this case, but we can say, look, there's still a very high probability that this belongs to class 2. Okay, and as I said, similarly with the male-female classification, I mean, there are cases where even though we assign it to one of the classes, the confidence or how sure we are that it's assigned to the right class may be very important, and that's where you can use the probability. So here is just a plot of these decisions that we can make for a classification. And we can use this plot to estimate various aspects of classifiers if they use the Bayes decision rule. And again, as I said, this is a bit more theoretical discussion about such classifiers. We'll have to discuss how these classifiers actually estimate the probabilities, which is the main part of these decision rules, but we'll get to that. Okay, so what I'm plotting here is the probability of y given x. Okay, the value of the probability of either y equals 1 or y equals 0. So for this is y equals 1 and this is y equals 0. And so this is the probability of the class label, and this is x, right? Let's say x is a one-dimensional, but x could be, of course, multidimensional. And we can see that we have some probability for y equals 1 given x, and we have some probability for y equals 0. And there is a case where they overlap. So in this case, we have positive probability for both. We always have a higher probability for one class versus the other, but we know that it could also come from the other one, so we are likely to make mistakes on that domain. So basically, I mean, even if we have the optimal classifier, as I said, sometimes the samples themselves are not enough to tell us the outcome, right? If I just measure the height and weight of individuals in this class, there's no way for me to accurately decide if they are male or female. I can, as I said, I can get a better probability, but I will definitely make some mistakes, even if I have the optimal classifier, just because there's a big overlap between them, as we see here. Okay, so we can still make a prediction on the overlap, but we know that at least some of these predictions will lead to errors. And this is called the risk of the classifier, okay? So the risk is the expected or the amount of error that we are going to get given the samples that we have. So in this case, the risk is the minimum value of the two distribution. Why the minimum value? Because the maximum we take as the prediction. So the risk is the mistakes that we make, basically. So in this case, the risk is the minimal value of deciding on 1 or deciding on 0. Okay, and we want to right and given the divided by p of x. Usually we ignore that, but basically this is the for each point, basically this is the probability that we'll make a mistake, right? I mean, the probability that we'll make a mistake is 1 minus the probability that we were correct. And now one thing we can do with this risk is we can actually find the overall risk, not just, so before we talked about risk at a specific location at X, we can also talk about the overall risk of the classifier. So let's say, again, I'm building a classifier for the class based on height and weight. I can tell you what is the overall error that I expect, maybe 20% of the students I'm going to get wrong, or 15% of the students. How do I compute that? I'm computing the expected risk, right? So expected risk, this is the risk that I expect to see on a random individual. What is the expected risk? The expected risk is an integral or summation if it's a discrete, like in the class, we have discrete variables, but generally speaking, it's an integral over all the points, and we just integrate or sum the risk for each point. And we said for each point, it's basically the minimum of the decision we are going to make, because the maximum is the decision, so the risk is the error that we're going to make. And this is something like P of y equals 0, P of 0 plus P of, I mean, this is not function of x, so we can take it out. And this is just the integration over the probability of x. Now, of course, in most cases, we don't know, or it's not trivial to compute this, but sometimes we can compute it, and it's good because sometimes the risk is something that we want to tell the users that, you know, this is a classifier, but I also can tell you that this classifier makes 20% errors or 15%. Sometimes this is useful. Sometimes people just want the classifier, the best classifier you can get. But in this case, it also tells you the so Daniel, is anybody monitoring? I see a lot of questions in the chat. Is anybody monitoring them?
Yeah, sorry, I'm writing this Piazza post to release homework 1. I mean, I encourage people to put their hand up instead of writing in the chat.
No, let's have a TA or one of them. I mean, we have a number of TAs on this call that they can monitor. I don't know who else is on this, but I would love, I want one of the, I mean, some of them can be answered by the TAs directly, but some of them, it's best to stop the lecture and ask me. And yeah, so there are a lot of questions about type 1. Yeah, this is exactly type 1 and type 2 error. Or another way to put it is type 1 and type 2 error. Basically, right, if you make type 1, again, if you have 2-class classification, you can do a false positive. It's also related to false positive and false negative, right? So false positive means that you say that something is positive even though it's a negative, and false negative is you say something is 0, but it's really 1, right? And we'll get to that in a second. Yeah, so if there's multi-color class, yes. So it's basically the sum of all the other classes if there's multi-color class. Let's say, Daniel, who else is on, let's say, who else? So Roger, do you want to be the one? I mean, if Daniel is not watching, can you stop me if there's any questions that I need to answer?
Sure, I'll do that.
Okay, great, thanks. Unless Daniel can do it, but if not, because, yeah, anyway. Thank you. So go on, keep posting. I apologize for not monitoring it before. I was hoping that, but we will, I mean, Daniel or Roger will stop me, and I will answer if there are questions that come up. Okay. So so going back to this type 1, type 2, and the loss thing. So the risk basically is computed for all the classes, right? So if, again, we are talking about 2-class classification, but if we have multiple classes, it's the sum over all the things that we reject. And we can compute the risk. The risk basically is the average error that we make on the data. Now, sometimes the average error is not what we really care about. Why? Sometimes we are better off making errors in one direction and not making them in another direction, right? I mean, the best example is medical cases where it's fine to make maybe a mistake. So not fine, but again, the example that people usually give is, let's say you do some diagnostic test, okay? So you have a diagnostic test, right? And of course, you want the diagnostic test to be as accurate as possible. And you can compute the risk or the error associated with the test. But the error might have a very different meaning in one direction versus another, right? So the diagnostic test, let's say for cancer or for another disease, let's say even, COVID-19, right? If the error is an error that is something called a false negative. So basically the test tells you that you don't have cancer, but you really have cancer. That's a pretty problematic error because now you took the test, you don't think you have cancer, so you're not going to do anything. Maybe you're going to take another test in a year or 2 years from now, but you'll be well off. And during that time, the cancer, of course, can progress, or similarly COVID and so forth. So this is a pretty problematic or very problematic mistake. If you take a test that has a false positive result, basically it tells you that you had cancer, but you don't really have cancer, or it tells you that you're infected and you're not really infected, that's, of course, devastating, right? You feel very bad. But usually, for example, in cancer, what you do is you do some more test, right? You do a biopsy, you do something else, and then you find out that the first test made a mistake. Okay, or in COVID case, you know, you don't have any symptoms, so you quarantine for a few days or 14 days, and you go out. So of course it's not great, but at least you didn't suffer the consequences of having a false negative. So sometimes false positives are actually much more or much better than false negatives, and sometimes it's the other way around. The loss basically takes into account not just the number of the errors, but also how much weight I'm putting on the error. And why is that important? Because using this, you can, again, the whole idea here is that you can find, or if you have different ways of designing your classifier, such that, for example, this classifier has on average a lower error than another classifier, then we will say, look, yeah, I would like to use a classifier that has on average lower error than the other classifier. But that's only true if you think that the errors in both directions are the same. If the errors in both directions are not the same, if you care more about one error versus the other, then rather than computing the risk, you need to compute the loss. And the loss basically is the weighted version of the risk, where the weight is related to how much we care about this mistake. So for example, in this case, we can say that this is loss of 0,1. Loss of 0,1 means that it's really a 0, but you said 1. Okay, so for example, in cancer, you really don't have cancer, but I'm telling you that you have cancer. That's not good, but we said maybe there's other ways of finding out. So maybe that will be pretty low, but loss of 1, 0, this is if you have cancer and I'm telling you that you don't have, maybe that's something that you want to avoid. So in that case, you will take a classifier that maybe on average does worse than other classifiers, but it's doing better for the vision that you are interested in. Okay, so this is called the loss function, and loss function weights differently the two sides of the arrow. And again, the main reason we talk about it is this is a way for you to decide which classifier is better for you. If you have a lot of classifiers, right, they can have the same risk but very different loss, or they can have different risks and also different loss. So that's something you have to take into account when you select the classifier. Okay, so these were all theoretical consideration. And again, I'm hoping that Roger or Daniel are monitoring the chat. I see there's a lot of things in the chat, but hopefully nothing major.
There's a lot of confusion on whether or not the area under the curves a couple of slides back is should sum to 1.
Yes. So again, I mean, it's, yeah, so yes. So the answer is yes, the probability of y over x has to sum to 1, but only if we, I mean, so, okay, so let's go back here. This thing has to sum to 1. P of y given x has to sum to 1, but this is of course related also to P of x. So this has to be weighted by P of x. So usually what we do is we ignore P of x. We don't compute that, and we just basically, so in that case, this will not necessarily sum to 1, but then we normalize it again by just making sure that, right, that let's say we have two probabilities, P1 and P2, we just say that, right, P1 equals P1 over P1 plus P2, and P2 equals P2 over P1 plus P2. So it's, yeah, but in general, yes, probabilities for a specific, for all the labels in a specific point have to sum to 1. If you compute the full probability. In most cases, again, we don't care about P of x. The only thing we care about is the ratio between the two predictions. So, and then in that case, we just use the numerator, and the numerator, of course, doesn't necessarily sum to 1. Good. Daniel, anything else, or we're okay?
I think that's the majority of it. Jason says, but the conditional probability is still a probability distribution.
Yeah, but when you, yeah, it's a probability, but so it has to be between 0 and 1, but it doesn't have to sum to 1, or it's a specific location. Okay, so let's move on. And again, if I can talk about more, or we can have, you know, post on Piazza a specific question. I'm happy to answer it in more detail. Okay, so this was a more theoretical question. As I said, we will instantiate it, or we will show examples of using Bayes rule later, including today. But more generally, I wanted to say that methods that use Bayes' rule are one type of methods. Basically, these are called generative methods, and they use a probabilistic model. And they are good, and sometimes they work well, but they are not usually the most successful ones. Now, as we said, the advantage of using probabilistic models is that you can compute confidence, you can compute loss, and so forth. The disadvantage is that you usually need to make very strong assumptions that don't hold in practice. Okay, so we're going to cover in this class a lot of different classifiers. In fact, most of the lectures from now on, or regression models, which can also be used for classification, but most of the lectures, including neural network, logistic regression, support vector machines, almost all the lectures in the first half of the class are going to be on different classifiers. These classifiers are different. Each one has a different method, but they can be divided into a sets of three major directions in classification or in their types. The first is what we're going to talk about today, called instance-based classifiers. Instance-based classifiers usually don't learn model or don't learn parameters from the data. They just use the instances or the points to do the classification, okay? And we'll show an example today. These are good because they don't make any assumption, but they are bad because they don't generalize the data very well. Basically, they just use the data. So advantages, disadvantages, of course. The second set of methods are generative methods, and I already mentioned that a lot of these use Bayes' rule. The advantage of them, as we said, is that if you can actually determine the probability, the parameters for the probabilities, you're going to get the optimal classification. There's no better way of doing it. The challenge is that it's almost impossible to really learn a good probabilistic model. For example, what is the joint distribution of pixels in a cat image, right? I mean, it's very hard to come up with a model that will accurately describe all of the pixels that we expect to see in an image of a cat, right? That's not trivial to come up with. So I will talk about methods that simplify this or come up with ways to simplify, but once you simplify it, you also lose some of the accuracy. And in that case, you lose, I mean, the classifier doesn't work as well as other classifiers. The third type of classifier, which is I think something we'll focus about the most, and also the most successful one nowadays, is something called discriminative classifier. Discriminative classifier forgets about the data and forgets about well, of course, it uses the data to learn parameters, but once it learns the parameters, it does not use the data anymore, unlike the instance-based classifiers. And unlike the generative classifiers, it does not try to learn probabilities. It just tries to learn a discrimination function, basically a plane, a line, something that if you're on one side, I will say you're in class 1, and if you're on the other side, I will say you're in class 2. And this can be sometimes extended to multi-classes. Sometimes it cannot, but most of the discriminative classifiers can work in multi-class classification problems. Okay, so this is the three major classes. As we said, instance-based, we're going to talk today. Generative, we'll talk later. And most of the methods we'll discuss are going to be discriminative-based classifiers. Before we talk about classification or specific classification algorithms, a few general things that people usually gloss over but are very important. In fact, sometimes they are more important than the classifier itself. Okay, and this is something that hopefully in the second problem set you will see, or at least some of it you will play with and see for yourself that these are very important things, even though we usually don't spend too much time on them in classes, we just assume something simple. So these are general steps that you need to do for all of the different classifiers, okay? And they can have a big impact on the success. Okay, so 4 different things that we need to take into account. The first is something called feature transformation. What do we mean by feature transformation? If you take a set of cats and dogs, right? These are images. Each image is a set of pixels. Do we use the pixels as the input? Do we input to the classifier a 2D matrix? Do we input a 1D vector that takes the first row, the second row? Maybe we take the first column and the second column and so forth. How do we represent this input to the classifier, right? The classifier can deal with numbers, usually vectors, maybe matrices, not more than that. But what if we have text, right? What if you want to classify documents? How do you represent that data to a classifier? How do you represent a text document? That's not trivial because usually classifiers don't deal well with words. They deal well with numbers. Or most of the classifiers we'll talk about are based on dealing with features that are numerical. So how do they deal with words? What if you have discrete variables? What if you have continuous variables? What if you have categorical values, right? So if you classify and you have cities, Los Angeles, Denver, I don't know, Pittsburgh, New York, and so forth. How do you represent these in a classifier? There's no relationship between them or no ordering. So these are all things that are very important and related to feature transformation. As I said, we will let you play or try some of these in the problem sets, but these are things to consider. Let's see. So that's the first thing. So feature transformation, taking the data and making it comparable with whatever classifier you want to use is the first step, very important step. So the way you represent the data, and we'll talk about it more when we talk about text classification, can have a big impact on the outcome. The second is, of course, specifying the model, right? So we are going to talk in this class about a lot of different classifiers. You will have to select one of them, or maybe two. I mean, there's a limit. I mean, and we're only going to present a relatively few. There are hundreds of them. So you will eventually have to select a classifier. And even within a classifier, you will have to make decisions about some general things. For example, if you use neural networks, you need to determine how many layers you're going to use in the neural network, how many nodes in each layer. If you use a Gaussian or if you use some probabilistic model, you need to determine which probability distribution you're going to use. If you use logistic regression support vector machine, you may need to design feature transformation methods. So even if there is a method that you select, decision trees, you will need to decide how many layers and so forth. So even after you select the classifier, which is an important question, there's something called hyperparameters that you need to set, and these will not be something you learn from the data, or at least not directly. There are ways, we'll talk later in class about how to estimate them, but these are not necessarily something that the algorithm tells you how to learn. You'll need to somehow either fix them or sometimes just make an assumption about, I assume that this is distributed as a Gaussian, this is distributed, I don't know, binomial, this is a multinomial, this is some exponential function, and so forth. So these are things that you'll need to decide. Okay, so this is the algorithm selection. So you'll have to select which one and then and make some general decisions about the algorithm. The next step, and this is true for almost all of the classifiers, maybe except for the one we are going to talk about today, which is k-nearest neighbors, where we don't really need to do this. But for almost all the other methods that we'll talk about, you will have to do a parameter estimation. So each of these models have some set of parameters associated with it. And this is what we usually call machine learning. This is where you're going to take the data that you have and the model, so the way you transformed it in step one, and the model you selected in step two with all the specifics that you set up, and then try to infer or learn from the data specific values for the parameters of the model. So each model will have its own set of parameters and they will have their own meaning. And the goal would be to try to take the data and the model and learn the values of the parameter. So this is the third step. This is what we are going to mainly focus about in this class, how to take whatever data you already transformed and whatever assumption you have about the model or which model you select and learn parameters for that model. Okay, this is the heart of the class, but it's not the only thing that would have an impact on your result. The final step is optional, although sometimes very useful, and this is called feature selection. Sometimes you can do it before all of the other steps, or at least after step one. Sometimes you need to do it at the end and iteratively update that with step three. This is called feature selection, and this is something that has to do with which of the inputs you really want to use. So maybe if you look at the image data, right? Maybe we just want to take out the dog image out of the entire image, somehow segment the image and take just the animal part and remove all the background because the background is confusing. Or I don't know, if you have stock values, maybe you don't care about most of the stocks, maybe only some of them are important. Or if you do biology classification and you want to predict if someone has cancer, you only want to select a subset of the genes. Okay, so this is called feature selection. Feature means that these are some of the inputs that we care about and we don't care about the other inputs. And sometimes this helps because the more inputs you have, the more parameters you need to set, and this can lead to something called overfitting, where you basically think that something is important, but it's not really important. So so feature selection is optional. You can use all of the inputs. There's no, theoretically, it's not, or at least in terms of the learning, that's not a problem. In practice, usually feature selection is good because we do have limited amount of data. If we have unlimited amounts of data, the thinking is that the classifier itself will already understand that some things are important and some things are not important, right? If I want to compute something is a cat or a dog, usually the background shouldn't have a big impact, right? So if I have millions of images, hopefully the classifier can find that out. But if I have very few, maybe it's better for me to do some type of segmentation before and just focus on this. Okay, so these are general things that relate or apply to any classifier, and some of them are optional, but some of them are going to be things we're going to do. Okay, so this is more general, and now just one word about why we call this supervised learning. The idea of supervised learning is that we have inputs that contain the label. Unsupervised learning is inputs that don't contain the label. In this case, we have the samples X, which are the images, and we have some teacher that for each X associates Y. Y is the label. It's a cat or it's a dog. And our goal is to learn a classifier, or it could also be regression if the output is continuous, that basically associates the samples with the correct labels. And this is usually done by setting a set of parameters, by finding values for a set of parameters. But regardless of how it's done, it's a way to generalize from the data to the labels that the teacher gives us. So it's a function usually that takes samples and output labels, and the goal is to have the labels as close as possible to the labels that the teacher gives us. And that's why it's supervised, right? There is a supervision on what are the labels for the samples. Okay, so this has been basically some high-level ideas on classification, and as I said, some things, even though we don't discuss feature transformation or feature selection, this can have a big impact on your success. But now let's go and discuss specific, or let's start with the first algorithm to do classification, which is k-nearest neighbors. And this is an instance-based classifier. So as I said, instance-based classification, we don't try to learn parameters from the data. We just use the data for the classification itself. Okay, so k-nearest neighbor, it's a simple but surprisingly efficient algorithm, and people use it still, even though it's a very simple, maybe one of the first methods people have thought about. And the challenge with k-nearest neighbor is that it's very hard to work with it in very high dimensional or very high input spaces because, as I said, it doesn't generalize from the data, it keeps all the data. So what does it do? So what k-nearest neighbor does is it selects the class label, or it predicts the class label based on the k-nearest neighbors. So k is the number, maybe it's 1, maybe 3, maybe 5. And if you want to predict a new label, let's say that we have these diamond shape, right, that we don't know the label for. So we have 3 classes in this image. We have the red circles, the triangles, and the squares. And now I'm giving you this diamond shape, and I want you to tell me what is this, what is the class of this diamond. Then I can look at the k-nearest neighbor and decide, right? If I use 1 nearest neighbor, then I will choose the red one, right? I mean, this is the closest neighbor is the red. If I use 3 nearest neighbors, then I will choose the square one, the blue squares, because 2 of the 3 closest ones are the squares. Okay, and there are some simple, I mean, you can decide what happens in case of tabs, right? If you have, if you use 3 and you have values from all 3, you can decide to randomly select one or to select always the red or whatever you want. Okay, so it's up to you. But this is the basic idea of k-nearest neighbor. Obviously, there is one parameter to k-nearest neighbor, which we don't learn, at least not initially. We will mention maybe how we can learn it, but generally, you have to define as a user the parameter k, which is the neighbors that you have to take into account. And once you define k, basically, and you get a new sample, you just compute the distance from that sample to all the other samples that you have. You pick the 3 nearest neighbors, and you take the majority vote for the class to be there. Or to predict as their neighbor, okay? So this is extremely simple method. Surprisingly, it works reasonably well in many cases. The nice thing is it doesn't make any assumption, right? We don't assume any probability. We don't assume any distribution of the data. We don't assume anything about the data. We just use the data as is. We do need to determine, or we do need to come up with a distance or similarity function, because in order to define the neighbors, we need to have a way of determining who is close to us and who is far away. So either a distance function or a similarity measure, which you have to assume. And the big thing is that we need to assume, or we need to state what is K, okay? So that's the big challenge. So what is the impact of K? Usually when you increase K, the classification becomes a bit smoother, basically, in the input space. Basically, you don't jump around from one class to the other if you move a little bit. So let me just show you some examples. So hopefully everybody sees I selected some samples, right? So we have a three-way classification problem, X, circles, and pluses. And we can look at the influence or the impact of 1 nearest neighbor, 3 nearest neighbor, and 5 nearest neighbor. Okay, in this case, in terms of distance, I'm going to use Euclidean distance, but you can use any other distance. So this is what happens when you use 1 nearest neighbor. It's not easy to see, but for example, here, you have this green one. And so if you move a little bit here or a little bit here, you just move to red, and here you're closest to the green one. Here you have a patch of green, another patch of green. This is a patch of blue. It's hard to see a patch of blue and another patch of red. So things are very fragmented in some sense, right? Because you just look at the closest thing to you, but you can find that classification. When you have K equals 3, things become less fragmented. So we have a one big green area here, another small green area here, but this is all red, this is all blue, and this is all red. So much fewer subsections compared to this one, but still we have some sections. And when K equals 5, we have this is all red, this is all green, this is all blue, and we have another red. So basically we have 4 segments here compared to much more segments before, right? So as you increase K, the number of segments or the number of divisions for the input space becomes smaller and smaller, or the input space becomes smoother because you get more locations that are going to have the same nearby, that are going to have the same result. Okay, so this is the impact of K. Of course, this doesn't mean that this K is better or this K is worse, but this is just a way to. And you can see, right, in K equals 1, you have a lot of fragments. In K equals 3, things look smoother, and K equals 5, it's even more. Okay, so how do we select K? Anybody has an idea of how to select K? Right, because K, I mean, the distance function, usually it's a matter of the type of data that we are going to use. But how are we going to select, or what's an idea of how to select? How can we select K? Yeah, okay, so I see the answers already in the chat, which is exactly what I was looking for. And this is a concept that I would like to introduce now, although it will go with us throughout machine learning. In fact, extremely useful concept if you haven't heard about it. We will define it formally a bit later in class, but you will use it in the problem set as well, so it's good to know. And this is a concept called cross-validation. Cross-validation means that we take some of the data, we use it for learning the model, and some of the and we leave some of the data out, and we use it to test the model. This is a way to test how good the hyperparameters or the decisions that we make are for the data that we have. For example, in K nearest neighbor, let's say that we want to compare 1, 3, and 5. So we can use K equals 1, we can use K equals 3, or we can use K equals 5. Okay, so there's 3 different options. What I can do is divide the data that I have into 10 bins, basically. So 10% of the data is each bin, okay? I can use 90% of the data for learning and 10% of the data for testing. What do I mean by testing? I basically look for the K nearest neighbor for this 10% using the 90% that I'm using for training, okay? And then I can check what will be the prediction for 1, for each of these 10%, what will be the prediction for 3, and what will be the prediction for 5. I know the answer because this is part of the training data, so I can decide which one is working better, right? 1, 3, or 5. And I repeat that 10 times because each time I leave another 10% out, I use them for the classification, and I use the 90% for the prediction. After I do it enough times, let's say I do it 10 times, I can ask on average, which classifier did the best. So maybe maybe one did the best for 8 out of the 10, and 3 did the best for 2 out of the 10. But on average, I can say that one nearest neighbor is the best for my data. And this is how you select the K. Basically, there are other ways of doing it, something called train test, where you divide the data in advance. But usually cross-validation is the best because it allows you to use all of your data both for learning and for testing. Because each time you divide it differently, you learn from one and you test on the other. This is something that we will do a lot for hyperparameters. Hyperparameters, as I said, are parameters that we don't learn directly from the data. We don't write like in MLE, we learn the probabilities directly from the data, right? We take the data and compute some values of the data, and we get the MLE. In this case, K is not something that we can learn directly from the data. It's not like if I see these images, I know that K is 5. We need to use the labels for that. So this is done using cross-validation. Or the hyperparameters for that are learned through cross-validation. Okay, so this is the idea of cross-validation. Again, very general. I'm talking about using it for K-nearest neighbor, but this is something that we can use for other things as well. Any questions about that, about K-nearest neighbor? I mean, hopefully everybody understood the method itself, right? So again, K-nearest neighbor, you just select K. We said we can do cross-validation, but you can just set K to be 5. Then when you get a new point, you just compute the distance from that point to all the points in your input space. You find the 5 closest points, and you take the majority vote as the label. Now, I should say the problem with that, of course, is that if you have millions of samples, this becomes very, very time consuming because each time you get a new sample, you need to compute distance to that. There are ways to do something called approximate K-nearest neighbors that can work very, very fast. So they have different data structures where they sort things out, and they have, so they are, and they are pretty reliable. So we did some tests in the past about approximation methods for K-nearest neighbor, and they work pretty well. So, you know, if you compare them to exhaustive search, they will give you more or less the same results for most of the cases. So there are ways to extend K-nearest neighbor to much larger data sets. Okay, so if there's no questions, then let's do another quiz on K-nearest neighbors. So I'm going to release 2 questions on K-nearest neighbors. And let's do them and talk about it. So I released KNN1 and KNN2. Again, just to reiterate, there's no grades for this. It's just to see very quickly that people are okay with the concept and the basic ideas. You know, don't spend too much time. Just try to answer it, and that's it. Okay, so 20, 30 more seconds, and we'll discuss this. Okay, so these questions are really about the concept of nearest neighbors. It's not so much about the classification itself, but what does it mean that we have nearest neighbors? So the first question is that we are doing a 2-class classification, 0, 1, and we use 1 nearest neighbor and 5 nearest neighbors, and both of them tell us that the majority of our neighbors, when we have the nearest neighbor to us is class 0, and of the 5 nearest neighbors, the majority are class 0. The question is, what will be the result of a 3KNN, or what is the majority from our 3 closest neighbors? And the answers most of you selected is that it's impossible to tell. Why is it impossible to tell? Because we know that your closest neighbor is 0, and we know that of the 5, at least 3 are 0, but we don't know necessarily that the top 3 are, 2 of them are 0, right? It could be that the top 3 has 2 1s and 1 0, and then the next 2 are also 0. So 5 KNN would be 0, 1 KNN will be 0, but 3 KNN will be 1. So the answer is based on the information that I gave you, it's still impossible to tell whether the result of 3KNN will be 0. Okay, so this is the first question. The second question, a bit more involved. I basically says that I'm allowing you to use, in a two-class classification problem, I'm allowing you to use not just odd case, but also even case. Usually we don't use even case, mainly because most of the time we apply this to a binary classification problem. If we use an odd case, right? So if we use an odd number, then we are guaranteed to have an answer. If we use even, we can have ties. But in this case, I'm saying that we can have ties. And if we have ties, then the classifier is not telling you 0 and 1. It tells you that you have a tie and represent it as 2. So now it says that for k equals 2, there is a tie. So we know that the first two neighbors, one is 1 and one is 0. Otherwise, you wouldn't have a tie. And for 4, we output 1. Now, if for 4 we output 1, it means that most of the 4 nearest neighbors are 1, right? So most is, it could be 4, it could be 3, but it could not be that we only have 2 neighbors in the top 4 that are 1, because otherwise it would be 2. So at least 3 of the top 4 nearest neighbors are 1, which means that also at least 3 of the top 5 nearest neighbors are 1. Okay, and if at least 3 of the top 5 nearest neighbors are 1, then the answer is of the 5 nearest neighbors is going to be 1. Okay, so in this case, so in this case, the answer is 1. So basically, the decision would be 1. Okay, hopefully everybody is okay with this. So this is pretty simple, hopefully. So let's go back to our lecture. Okay, so as I said so far, it seems like k nearest neighbor is just a very, I don't want to say arbitrary, but a very simple way of deciding on the output. We didn't show any motivation, or we didn't show any derivation or any theoretical consideration of why this should be a good classifier. We just said, look, select the classifier based on the most nearest neighbors, right? But why should that work? Why is that a good idea? So it turns out that you can actually view k nearest neighbor as something that is trying to optimize the base decision rule. We already said that base decision rule is an optimal classifier if you have the right way of defining the probabilities, okay? What I want to argue now is that KNN basically tries to approximate the base decision rule with a very specific assignment of these probabilities. So what KNN is trying to do is compute the base decision rule probabilities, or the probabilities of X, the probability of Y given X, and the probability of X given Y, the probability of X given Y, the probability of Y, and the probability of X in the local neighborhood. So rather than compute it globally, right? Usually we expect the probabilities to be global. So the probability of X everywhere, the probability of Y everywhere. What k-nearest neighbor is doing is computing these probabilities on a local neighborhood and using these computations to make the decision. Or basically, once you compute these probabilities, it uses them to make the classification. Okay, so again, this is just an approximation of the base decision rule, but if you believe the approximation, then, this is just an approximation of the probabilities, but if you believe the approximation of the probabilities, then you get back the base decision. Okay, and how is this done? The key point, and I think is to consider, I mean, everything else is easy, but the key point of this is to consider the uniform distribution of the area that the k-nearest neighbor is using. So let's discuss this. So in k-nearest neighbor, right, we define, let's say we have some point that we want to classify X. We define a ball around X that contains k neighbors, right? So let's say k is 5. This ball contains 5 different neighbors, okay? It doesn't matter which class they are. right? This is how we define the ball. We first select X, which is the point. Then we define a ball around X that contains 5 points, right? So let's say 7, so it can, let's say K is 7, so it can be like this, okay? Now, once I define the ball, let's say I have K here. This is the input space. The input space is all of this square here, okay? And we have n samples. What is the probability of a sample to be inside the ball? It doesn't matter which class it is. What is the probability of a sample to be inside the ball? Anybody can tell me? Or you can write to the chat. Let's see. Yeah, absolutely, right? It's pretty simple. It's K over N, right? If you take a sample at random and you ask me whether it is in the ball or not, I will tell you that there is a K over N probability that the sample is in the ball. Now, let's assume that this probability is uniform within the ball. What does it mean? Any location in the ball can have a sample with the same probability. Let's call this probability P of X. What do we know about P of X? We know that if we sum P of X over all the ball, or if we take the integral over the ball of P of X, what will be the outcome of this integral? Or what is the sum of all the probabilities of a point in the ball? Right, this is K over N. That's what we said. The probability of being in the ball is K over N. So if we say that the uniform probability of any point in the ball is P of X, and we sum over all of these points, we should get to K over N. Again, I don't know what P of X is, but I know that the integral over P of X over all the ball is K over N. Okay, this is the key point for our discussion. So basically what KNN does is it tries to estimate the base decision rule of the probabilities within this ball. It ignores everything that happens outside the ball, or it doesn't try to estimate. But within this ball, it tries to estimate the probability of P of X, P of Y, and so forth. Okay, so this is the basic idea. And right, so this is the basic idea. We basically define P of X times V. So this is V, I mean, this is the integral. So if you look at V as the size, and because everything is uniform, right, you can take P of X out because the integral is over V over the ball, and X is uniform. So P of X times V is equal to K over N, which is the probability of being inside the ball. P of X, the uniform probability of any point in the ball. V is the size of the ball, right? It could be n-dimensional. And K over N is the sum of that, or basically the integral of that. Okay, if you believe that, then a lot of other things follow. Oops. Right, so if you agree on that, then most of the other things follow pretty straightforward. So if this is the case, then P of X is K over NV, and then you can do it for other variables. So we're out of time. So I will continue or finish this in the next lecture. Again, the critical point is this part here. Once you agree or believe this part, everything else follows pretty easily. But again, we'll go back to that in the next lecture. But the basic idea is that using KNN, we're trying to estimate the base probabilities or the probabilities, but within a specific subset. We don't try to estimate any global parameters. We just try to estimate local parameters. But if we do that, then the decision that we make, this selection based on the majority of the points inside the ball, is also the base decision that we would get. That's the point. And again, we'll get to that, or I will show you it more formally next time. Okay, so we're out of time. Again, I will repeat, don't worry if you didn't understand this part. You don't need it for the problem set. So you can start working on the KNN questions in the problem set without this. I will repeat this and explain it in the next lecture. So if you didn't understand it, it's fine, and we'll repeat it, okay? Good, so that's it for now. We're out of time, and I will see everybody next time. Again, if you have any other questions,